Learning objectives. At the end of this topic, you will be able to analyze angles subtended by an arc of a circle. Define concyclic points. Describe cyclic quadrilaterals. Introduction. Look at a circle with two equal chords. We know that the points of a chord other than the diameter of a circle cuts it into two arcs, one major and the other minor. If you take two equal chords, what can you say about the size of the arcs? If AB and CD are two equal chords of a circle, their corresponding arcs are congruent. The converse is also true. If AB and CD are two congruent arcs of a circle, what can you say about the chords AB and CD? Simple measurement shows that AB and CD are equal in length. Thus we can say the chords corresponding to congruent arcs of a circle are equal. Congruent in the sense, if one arc is put on the other without bending or twisting, one superimposes the other completely. Now let's verify this fact by cutting the arc corresponding to the chord CD from the circle along CD and put it on the corresponding arc made by equal chord AB. You can see the arc CD superimposes the arc AB completely. This shows that equal chords make congruent arcs, and conversely, congruent arcs make equal chords of a circle. You can state this as follows. If two chords of a circle are equal, then their corresponding arcs are congruent, and conversely, if two arcs are congruent, then their corresponding chords are equal. Here let's use the property of congruent arcs of a circle to prove a theorem. The theorem states the congruent arcs of a circle subtends equal angles at the center. Now we have to prove AB and CD are two congruent arcs, then angle AOB is equal to angle COD. To prove the theorem, let's draw corresponding chords from arcs AB and CD. As you can see, angles subtended by arcs AB and CD at center O are equal to angles subtended by the corresponding chords at the center. In this figure, chord AB and CD are equal. Since we've already seen the chords corresponding to congruent arcs of circle are equal, we already know that equal chords of a circle subtends equal angles at the center. Thus, angle AOB is equal to angle COD, and theorem is proved. How many types of arcs do you find in a circle? A chord divides the circle into two arcs. The shorter one is called the minor arc, while the longer one is called the major arc. If the chord is the diameter of the circle, it divides the circle into two equal arcs, each of which is called a semicircle. Next, we will discuss the theorem related to arcs. The theorem states that angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. Let's prove the theorem simultaneously for a minor arc, major arc, and semicircle. In the given figure, we have an arc AB. Consider any point C on the circle that's outside AB. Now here we have to prove angle AOB is 2 times of angle ACB. Before we start with the proof, consider the line joining point from C to center O and extend it to the point D within the circle. Consider triangle OAC in each of these figures. In each angle, angle AOD is the exterior angle of triangle OAC. Since the exterior angle of a triangle is equal to the sum of its interior opposite angles, angle AOD is equal to angle OAC plus angle OCA. Also in triangle OAC, OA is equal to OC since they are radii of the same circle. This makes triangle OAC an isosceles triangle. This also means angle OAC is equal to angle OCA, since angles opposite to equal sides of a triangle are equal. This also means angle AOD is double angle OCA. Similarly, in the triangle OBC, we can prove angle BOD is double the angle OCB. From these results, we get the sum of angles AOD and BOD is double the sum of angles OCA and OCB. This clearly shows angle AOB is double angle ACB. Hence, the theorem is proved. Remember, in case of major arc, the reflex angle AOB will be double the angle ACB. Now consider another point D on the circle in the same segment as point C. What can you say about angle ACB and ADB? The theorem states that angles subtended by an arc at all points within the same segment of a circle are equal. So we have to prove angle ACB is equal to angle ADB. By the theorem, angle subtended by an arc at the center is double the angle subtended by an arc at any point on the remaining circle. So we can say angle AOB is double the sum of either the angle ACB or ADB. Thus, angle ACB and ADB are equal. Hence, the theorem is proved. Here is an interesting property of angles formed by an arc in a semicircle. All angles formed in a semicircle are right angles. Let's try and prove this. Draw a diameter AB to divide the circle into two semicircles. Now consider arc AB. Take a point P outside AB on the circle and join AP and BP. By the theorem that states angle subtended by an arc at the center is double the angle subtended by the arc at any point on the circle. We have angle AOB is equal to 2 multiplied by angle APB. Since AOB is a straight angle, we get an angle APB is equal to 90 degrees. By the theorem, we also know that all angles subtended by an arc in the same segment are equal. This means angle AQB and ARP are also right angles. Thus, we can say all angles formed in a semicircle are right angles. Concyclic points. Consider 3 points A, B, and C. Let's join AB and BC. Next, let us mark the midpoints of AB at M and BC at B. Now let's draw a perpendicular at M. The line MN represents the perpendicular bisector of AB. Now let's draw a perpendicular at B. Here PQ is a perpendicular bisector of BC. The perpendicular bisector of AB and BC intersect at O. Join OA, OB and OC. What can you say about the lengths of OA, OB and OC? They are equal because any point on the perpendicular bisector of a line segment is at equal distance from the endpoints of the line segment. Since A, B and C are at equal distance from O. Since A, B and C are at equal distance from O. A circle drawn with a center O and the radius OA will pass through all the 3 points A, B and C. A point in this case A, B and C that lies in the same circle are said to be the concyclic points. Now let's prove a theorem. It states if a line segment joining 2 points subtends equal angles at 2 other points lying on the same side of the line containing the line segment, the 4 points are concyclic. Let's prove this theorem. Here AB is a line segment that subtends equal angle at C and D. We have to prove A, B, C and D lie on the circle. Let's use the construction we did earlier to draw a circle through points A, B and C. For proving the theorem, let's suppose that circle drawn through A, B and C does not pass through D but intersects AD at D'. Cyclic quadrilateral. Consider 4 concyclic points. What do we get if we join the points A, B, C and D? We get a quadrilateral ABCD. It is a special quadrilateral. All its vertices lie on a circle. A quadrilateral is a cyclic whose vertices lie on a circle is called a quadrilateral. It's called a cyclic quadrilateral. Now let's see a very interesting property of cyclic quadrilateral. Let's measure the opposite angles BAD and BCD. Note, their sum is 180 degrees. Now measure the opposite angles ABC and ADC. Their sum is also 180 degrees. Now consider another cyclic quadrilateral to verify the same result. Measure the opposite angles BAD and BCD in this quadrilateral. Note, their sum is equal to 180 degrees. Similarly, measure the opposite angles ABC and ADC. Their sum is also equal to 180 degrees. This way we can illustrate the theorem that in a cyclic quadrilateral, the sum of opposite angles is always equal to 180 degrees. We can also illustrate the theorem if the sum of opposite angles of a quadrilateral is 180 degrees, then the quadrilateral is a cyclic. Here is a simple quadrilateral, a square ABCD. We know that all angles of a square are equal to 90 degrees. This means sum of its opposite angles is equal to 180 degrees. Let's see if we can draw a circle that contains all its vertices. If you draw a perpendicular bisector of sides AB and AD, we find they intersect at the point O. If we draw a circle with center as O and radius equals OA, we find the circle contains all the vertices of the given quadrilateral. Through simple construction, you can also illustrate the quadrilateral is cyclic if the sum of at least one pair of angles is equal to 180 degrees. Summary. Let's summarize the topic. If two arcs of a circle are congruent, then the corresponding chords are equal. Conversely, if two chords of a circle are equal, then the corresponding arcs are congruent. Congruent arcs of a circle subtend equal angles at the center. The angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. Angles in the same segment of a circle are equal. Angle in a semicircle is a right angle. If a line segment joining two points subtends equal angles at two other points lying on the same side of the line containing the line segment, the 4 points lie on a circle. The sum of either pair of opposite angles of a cyclic quadrilateral is 180 degrees. If sum of a pair of opposite angles of a quadrilateral is 180 degrees, the quadrilateral is cyclic.